Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hello, I'm Cray, and on behalf of the Australian Water School, welcome to our second HEC-HMS webinar, where we'll be highlighting the powerful new features that have been introduced since our first HMS webinar back in 2019. We are excited once again to have the HMS development team with us today to step us through the new capabilities. Now, since our first webinar, we've had a lot of questions come in about how to use HMS in Australia, where it really isn't in common use at the moment. So after today's main presentation, we will follow up with some methods and resources that will allow you to import Australian meteorological data straight into HMS. So looking at the global spread of today's registrants, if you think of HMS as an American software package, it looks like we may need to rethink that assumption. We are showing interest from all around the planet. So for today's format, the presentation will run for about an hour. It will be followed by a live Q&A session with the presenters and panelists who you see here. We have Thomas Brauer and Michael Bartles from the HEC-HMS development team as presenters. They're supported by Matt Fleming, who will answer your questions in the background on the Q&A line while Tom and Mike are presenting. We also have Martin Jacobs, a power user from Pitt and Sherry, who will be providing an Australian perspective. He'll be supported by Chris Ryan of Catchment Simulation Solutions. They're the developers of the Storm Injector software that Martin will be highlighting in his presentation. Chris will be on board as a panelist answering any pertinent questions about Australian applications. Now, for those who are new to HMS, the hydrologic modeling system, it's developed by HEC, the Hydrologic Engineering Center of the Corps of Engineers. The HMS team is located in Davis, California, and we do have a couple of poll questions here for the audience around their whereabouts and the Corps itself. So we've got question number one, which is about the HEC offices, which take up the second floor of a building in Davis. Is it located above a cookie shop, a shavery, a kava bar, or a wine bar? And then we've got question number two, which deals with how old the Corps of Engineers is. So if the presenters and panelists can all turn your cameras on, we'll go over the poll results and introduce you to the audience. First of all, let us know where you're coming to us from today, and do you know the answers to these questions? Let's start with Tom. Are you at home or in the office today?
Yep, I'm working from home today, but I'm about a block away from the Hydrologic Engineering Center. So do you want me to go ahead and answer the poll questions now?
Yeah. Well, let's let Joel close that poll first, and then
okay.
And then maybe you can come back on. Mike, are you coming to us from Davis, or where are you sitting today?
Today, I'm actually sitting at home. I live about 10 minutes north of Davis. I would be very surprised if anybody on the line knows the answer to this one, but it would be cool nonetheless.
Yes, it would. All right, and let's see if we've got, let's have Martin and Chris say good day as well. Martin, where are you coming to us from today?
Good morning, everyone. Yeah, I'm from Brisbane and working with a consulting engineer here.
Good.
And I'm in Sydney.
Excellent. All right, so now let's, and Matt, is Matt on the line as well?
Yeah, I'm here. I'm calling in from HEC.
Sorry. Matt, yeah, okay, so you're at HEC right now? Okay, so you are sitting above which of these locations? So Tom, you want to answer that question?
Well,
shot?
I thought there were two right answers there.
And that's a trick question for all of you. Tom, any stabs at it?
I just remember when they were installing Insomnia cookies, suddenly the library started smelling like cookies, which was a bit distracting. So I'd go with those, although I think they might all be true.
Hey, oh, there you go. All right, I was going to test you. They are all true. I just pulled that off of Google Maps, and it's all of the above. So that's all of the above. That's what we've got there. So yes, and if you've ever been there, it's unmarked, pretty much unmarked. It's up on the second floor. And the second question then, Australia, United States, or the Corps of Engineers, look at that. It is true. The Corps of Engineers actually predates the formation of the United States or the Australian governments. And there's quite a history there. All right, thanks everyone for that. We will get back to the presenters momentarily. Just as a warning, we're going to step through things fairly quickly in the interest of time, but all attendees will have access to this recording to pause and go back through it at your own pace. And I've also set up this webpage that you see here at surfacewater.biz/HMS, and it's got some background material, including a link to the previous Australian Water School webinars, today's presentation slides, and some additional resources. Now, if you are brand new to HMS, I would invite you to go back and watch this first webinar, since we described some of the differences and the overlap between rainfall runoff routing models like HMS and hydraulic models like HEC-RAS. We've also got a demo of the storm injector interface that Martin and Chris will be presenting here. And on the website, I've also included some of the webinars and links from the HMS team. So you'll see some links here to their support pages, and these are some excellent resources that cover a lot more detail than we'll have time for today. Some webinars that they run, you may wish to subscribe to these ones as well, and just have a look at some of this background material. There's a lot out there for you. Finally, I've included some background about the core and the HEC team, including answers to today's poll questions. This is the office here. You can see a map, and you see the core offices here. The HEC office is nestled between Bizarro World and the Ho Ho Market, surrounded by coffee shops and sushi shops and pizza. But right there, you'll see the answers to today's poll questions. Looks like this one's just outside of the office, but part of the same building footprint there. So maybe 3 of the 4 are actually below the core offices, which you see here. So there's the wine bar and then an unmarked door that leads to the staircase that comes up to the HEC offices. And then also a little bit more background here on question number 2. And I've got some resources here as well about the HEC organization. And you can see some of that right here, the history, the chronology, and a whole bunch of other resources about the HEC team and the other software and publications that they put together. Now, if you like what you see today and you want to do this yourself, come along to our upcoming course in November, where you'll get the chance to create an HMS model live and on the fly while the instructors are supporting you. So we'll get you through the session, answer your tech support questions, and to get everybody running a model that you'll be able to interrogate and test out and fix up and view the results just like you'll see the experts do today. We'll run 2 sessions, initially covering a basic model setup, and then anyone who wants to dig into the Australian rainfall and runoff approaches in HMS can join an additional session where we will use the tools you see today to pull in the Australian data. So course registration details will be sent to all webinar attendees as that date gets closer, and we will post them on the resources website as well. So with that introduction, let's turn the time over to Michael to kick things off for us.
Yes, I'll actually kick it off here, but I do want to say thank you. I'll let Tom also say his piece here. Thank you for inviting us to make this presentation. Really looking forward to it. We've been practicing for a while, making sure our software is up to snuff. So we're looking forward to doing part 2 of modeling with HEC-HMS, showing off a little bit of what we got today. So today within the presentation, Tommy and I are going to go back and forth a little bit. We're going to have a couple of slides. We're going to give a little bit of a brief overview of HMS and some of the updated documentation, but we really want to get to demo additional features that we've made since the last time we presented, which was in October of 2019, I think it was. So we've done a lot since then. Tommy's done a lot. He's been adding 95% of the stuff, but a lot of really cool new GIS stuff. Really excited about the expression calculator, the way that we handle gridded data. Tommy's got a new automated forecast tool, which is hopefully going to blow your minds. The way we visualize results and 2D flow enhancements in there. And we'll wrap it all up with a little bit of discussion regarding upcoming enhancements.
All right. Well, thank you, Mike. So we'll just go over HMS briefly. It's a hydrologic modeling system. You can download it for free on our website. You can see our website here with the download links. So navigate there if you're looking to download the latest version. We're averaging 50,000 downloads per year as of recent. I think that can largely be attributed to a lot of the new features that we're adding. There's a lot of excitement around the program now because I think the speed at which we're delivering these new features is really helping our customers. So we're seeing a major uptick in downloads, which is great. We're distributing for the Windows, Mac OS, and Linux platforms. So if you're on any of those computers, please try it out and test it on those different systems. That's been something that we've done, updated as of recently. And then our latest release version is version 4.8. We have a 4.9 beta that we'll be demoing today. That's pretty close to being released. So if you like just a little more stability, you can stay in the release versions. And if you like to test the latest and greatest features, feel free to download and test the 4.9 beta and give us your feedback. I'll mention our documentation. We recently went through an effort to put all of our documentation online. So traditional documentation like our user's manual and technical reference manual, those are all online now and you can look for them there. I'll also mention some of our new documentation formats, tutorials and guide, and YouTube videos. These we're updating pretty continuously. So if you tune into our various channels, you can see the latest tutorials and guides and YouTube videos. And I highly encourage that if you want to see easy introductions to different features, to new features. All right, without further ado, I'll jump into a demonstration. We're going to demonstrate some GIS features today. We're going to delineate a basin, and then I'm going to set the model up and try to run a forecast on it. And then once I do that, we'll pass it to Mike to show you some spatial results and to do a two-dimensional flow compute. Okay, this is HEC-HMS. I've already created a project just to streamline our demo today. So I have a project created in my C projects directory. It's named Punxsutawney. The first thing I'm going to do is to create a terrain data object. So I've gone to terrain data manager. I'm select new. I'm going to name my terrain NED 10 meters. I'm going to navigate to the terrain file. And then I can have an option to select a vertical unit system. My vertical units are meters, so I'll just use that and hit finish. All right, so I've added my terrain data. The next step is going to be to create a basin model. So I'm going to name my basin Mahoning Creek. I'm going to create that basin model. And now I'm going to link the terrain data that I already added to the project. When I do that linking and hit save, I'm prompted with a dialog about selecting a basin model coordinate system. I can optionally select a coordinate system, but if I hit the skip option, then it will assume the coordinate system of my terrain data. So I've already reprojected my terrain data into UTM coordinate system. So I'm going to hit skip. And it should assume that coordinate system. We wanted to use UTM coordinates in meters today for our international audience, just to demonstrate that HMS can be used anywhere in the world. So now if I go to the GIS menu coordinate system, I can verify that it is indeed using UTM zone 17 north. So for our international users, we recommend using the UTM zones as your projection. For those users in the United States, we often use the standard hydrologic grid projection, which HMS has widespread support for. Okay, next step, I'm going to go down this GIS menu. And a lot of HMS users who have used the program in the past are probably familiar with the GeoHMS utility. And what you're going to notice is that this GIS menu essentially replaces GeoHMS. So if you've tuned into HMS in the not too distant past, you'll see that we have formally decommissioned GeoHMS. So if you're still using it, please consider coming over to HMS to do these GIS processing steps. And the biggest thing that I think that helps us is that this code is in a much more serviceable place than where GeoHMS was. So if bugs happen to come in, we can easily fix them. And then for the user, you have a tighter feedback loop when you go to make modifications to your basin. So all around, it's a good thing to have the GIS features in HEC-HMS. The first step on this GIS menu that I'm going to demonstrate is terrain reconditioning. So this is just altering the terrain that we started with to reinforce the hydrologic network. So I've opened the wizard. Before I go through it, I'll just pull up a tutorial and guide. Actually, this is from the user's manual, just to demonstrate the options that are within the terrain reconditioning wizard. And those are a smooth drop and a sharp drop, and you can burn them or build them. So building will raise the terrain grid cells and burning will lower them. The difference between smooth and sharp is simply there's a taper with smooth, so you can define a buffer and you can taper that drop. And then with a sharp drop, there's no taper, it just drops directly. So that's the short explanation. If you want to learn more, feel free to visit this page in our user's manual. I'm going to browse to a build walls file name and a burn streams file. Before I do that, I'll actually show you that in QGIS. I have it pulled up here so you can see I'm going to use this outline as my build walls and these rivers as my burn stream. So I'm just going to reference those same files in HMS. Okay, I've entered the parameters I'd like to use, and now I'm going to let HMS recondition the terrain. Okay, reconditioning complete. Now to show you what has happened to our terrain data, the reconditioned terrain layer has actually rendered in our map display. I have our map layers here. So what I'll do is I'll just zoom into the boundary of the watershed, and I can already tell that the cells around the boundary look a little different than they were previously. Not sure if you can see that, but I will just toggle the reconditioned terrain on and off, and hopefully it becomes apparent where that wall has been built. And additionally, the stream definition as well should be more clear now. So if I toggle the reconditioned terrain on and off, we should have better definition where our streams are. So that's the reconditioned terrain. And like I said, that just reinforces our hydrologic network and where subbasin boundaries are. So it's a good step if you have published watershed boundaries and streams. So I'm going to turn that layer off. Next step on the GIS menu, I'm going to pre-process sinks. This is going to fill in all of the low spots in the raster to create a hydrologically corrected DEM. So it'll just remove all of the low spots so water can flow from any grid cell to the outlet without falling into a pit. So I can see those locations here in the map. I'm going to go ahead and turn those layers off because we're going to move on to the next step, which is pre-process drainage. And what this will do for me is create a flow direction grid and a flow accumulation grid. Let's look at flow direction first. This is the flow direction grid. And for each grid cell in the raster, the water can flow one of 8 directions. And so this is just giving me a notion of which direction the water flows from any particular grid cell. And then if I look at the flow accumulation grid, this takes the flow, this is a derivative of the flow accumulation grid, and it gives a notion of how many streams, sorry, how many cells upstream of a particular cell flow to a given cell. So if I zoom in to say this cell, I can see there is 441 cells upstream. So that's the flow accumulation grid, and both flow direction and flow accumulation grids, they help us with watershed delineations and characteristics computations. I will zoom back out. Next, I'm going to use the identified stream step. And I'm prompted with a dialog to define an area for the stream threshold. So I'm going to use 50 kilometers squared, and all this is saying is that if there are 50 kilometers upstream of a grid cell, then we're going to call that a stream. So you can see here, everywhere where I've defined the streams is this orange line, and that just means that there's greater than 50 kilometers squared upstream of that particular cell. That's the identified streams layer. The next step will be the breakpoints manager. We're going to import breakpoints for our delineation. And I have a stream gauge shapefile that I'll select here. And I've imported my breakpoint right where the stream gauge is. I'll just show you real quick in QGIS, that same layer. So I can see here, this is a stream gauge, and this is my river delineation, my river shapefile. And so one thing that's nice about the breakpoint import option is that it will actually snap that breakpoint to the stream. If you were to manually identify that breakpoint, you'd want to make sure it's on the identified streams layer. I can zoom in and I can see that it is indeed on the identified streams layer. All right, we're all set for delineation. I'm going to go to GIS, delineate elements. I'm prompted with a few options. I'm not going to use all of them, but I will insert junctions, and then I'm going to delineate my basin. All right, this is my initial delineation. And from here, I have options to merge or split my subbasins and reaches. I'm going to do some merging in this lower subbasin. I want to have one subbasin down here. So this is something that's new that changed from the last time that we gave a presentation similar to this. At that time, you could only select 2 elements at a time. Now you see I've selected 5, and I'm going to merge them all at once, which is quite nice. And likewise for reaches, I can select multiple reaches and merge those. I won't get into splitting now, but if we have time at the end, I can show you how splitting has been enhanced so that you can split from anywhere in the basin, which is an enhancement from the last time we gave this presentation. From here, I'm going to rename a few of my elements now that I have the delineation that I like to move forward with. I'm going to name this one East Branch Mahoning Creek. We need a quiz question about Punxsutawney and why it's famous. So if anybody knows what movie was filmed in or set in Punxsutawney, Pennsylvania, feel free to enter that one in the chat. If you tuned into our last webinar, we might have given that answer away. All right, I've renamed the elements to my satisfaction. These are the names I'd like to move forward with, so they're good. The next thing that I'll demonstrate, it's parameterization, but it's also a GIS process. It's our new discretizations concept. So it's a way to discretize our subbasins. So I'm going to go to parameters discretization. I'm going to change the method to a structured discretization. And now I'm going to go to parameters structured. And for the projection, as I said today, I'm going to use UTM 17 North. So I've selected that for all of my subbasins. All right, so I've set my discretization. The next thing I'm going to do is actually compute the grid cells from the GIS menu. And if I enable this discretizations layer, I should now see my grid cells. Something a little bit funky happened here. I'm not sure what's going on there. Let's see if I can recompute. So override what I'm seeing there. Okay, it doesn't look like that's an option. I'll proceed with the demo. I'm not sure what happened there, but I'll just keep going and see if it causes me any trouble later or not. All right. So the next step is I'm going to turn my discretization layer back off, and I'm going to parameterize my canopy method. The canopy extracts moisture from the soil layer at the rate of actual evapotranspiration. So I parameterize my canopy. Next, I'll parameterize my loss method. So for initial deficit, I'll just use 0 because we're assuming that we're coming into the storm with saturated soils. And then for maximum storage, I'm actually going to demonstrate this new expression calculator feature that we have where I can sample from a raster. So I've already loaded this raster into HEC-HMS. Now my maximum deficit values are in millimeters. So I'm just going to multiply by, sorry, they're in inches. I'm going to multiply by 25.4 to get to millimeters. So you can see I've now done zonal statistics on that raster to come up with the maximum storage. And I'm going to do something very similar for the constant rate. So let me just start over down here. If I double click that, it'll add it to the expression calculator. I'll multiply it by 25.4. And then I have my constant rate values initialized. All right, canopy surface loss. Actually, we didn't do surface, we did canopy loss. Surface is optional. Next, I'm going to do my transform, but before I do that, I'd like to show you the new subbasin characteristics feature. So one thing we can do now is now we have GIS features in HMS, is we can do characteristics for things like subbasins, so longest flow path, centroidal flow path, basin slope, relief. So I have these characteristics which are great for parameterizing my basin. I can do the same for reaches, so parameters, characteristics, reach, and I've computed some characteristics for my reach, my single reach in the basin model. Now when I go to parameterize transform, I can use the same expression calculator, but instead of sampling from grids, I can sample from statistics that were computed in my characteristics computation. So rather than typing that in, I already have a formula prepared that I'm just going to paste in. And it looks something like that. So I'm going to calculate my time of concentration. And to initialize the model, I'll just use the same values for the storage coefficient. So I can just do that here. And my TC and R are the same values. So I'll hit apply there. All right, finally, I'm going to parameterize the linear reservoir base flow method. These parameters are best initialized and then calibrated against observed results. So I'm just initializing them now. Hopefully my knowledge of the basin will allow me to put some fairly reasonable initial values. I'm going to apply that for my linear reservoir baseflow method. Now there's just a few things left to do before I'm going to try to compute. I need to parameterize my reach. I'm using Muskingum routing. Okay. And then the last thing I will do is add observed flow down here at my sink. I have a discharge gauge already linked, so I'll just select that. Okay, so now I've gone through the whole basin development process. And in past webinars, we've added some meteorologic boundary conditions, and we did that using some vortex utilities, which are now actually in HMS. So if you want to see those in action in HMS, there's some tutorials and guides about adding and creating meteorologic boundary conditions. For today's webinar, I plan to demonstrate the auto forecast feature. So I'll go through that. I'm a little bit nervous because of what I saw earlier with the discretizations, but we'll just give it a try and see how it goes. And if not, Mike has some historic storms already loaded in HMS, and so he can show off some simulation runs and results. So let me just go through the automated forecasting steps. We're going to go to Compute, Forecast Alternative Manager, and select Auto. It's going to give me an automatic name for my forecast. I can select a basin model. I'm going to use Mahoning Creek. Forecasts have a look back period, and I'm going to just to make the data pool a little faster, I'm going to use 7 days, and then I can select from a few different, well, just one historic or real-time data source, which currently is real-time mesoscale analysis. And then here, there's also a forecast period, and we have a number of options here. And so I'm going to select all of these. And what this automated forecasting utility is going to do is it's going to stitch together the look back period to the forecast period and create a forecasting boundary condition for me. So this is just a faster way to spin up a run than what would have taken us to do by importing a bunch of data. So we'll see how this goes. Right now, we're reaching out to a server and pulling in real-time mesoscale analysis data, and then we'll jump to some of the forecasting products. Now we're retrieving high resolution rapid refresh, North American mesoscale, and global forecasting system. Now HMS is actually converting these from NetCDF to DSS. We're retrieving some flow data at our gauge location, and we're running a forecast. All right, let's view results for our forecast. And there I can see, it looks like our look back period is on target. This is fairly low flows. That happens to be real time right now at Punxsutawney on the Mahoning Creek. I can see that we're fairly well calibrated historic, but there's not a whole lot of action going on in the near future. So sorry for the lack of excitement in our forecast, but that just shows how quickly you can do a real-time simulation. As you probably noticed, most of our data sources are for North America, and would like to expand that to international data sources in the future. So if you're into real-time and you're into international data sources and you have something to offer there, feel free to reach out. I'll just mention that, and perhaps we can implement some international data sources there to make this a utility that people can use around the world. Okay, well, I think that's all I had planned. At this point, I'll pass it over to Mike. So Mike, if you want to take control, feel free.
Thank you, Tommy, for showing all these cool new features. Tommy's been working really, really hard at all this stuff. So you have him to thank for the program being as awesome as it is. What I wanted to show you in particular here, what we haven't done before is the ability to display, say, precipitation across the watershed. We've shown you computes before where you've been able to see, say, the runoff at this specific gauge location, right? You've seen this before. I can compare computed results in blue to observed results in black. That's a time series. That's cool. But I really want to see how precipitation was distributed. Every single one of these grid cells gets its own unique hydrograph that's applied to it since I'm using gridded precipitation. So what I can do is I go to the Compute tab, expand simulation runs, click on the actual simulation run of interest. Now I'm confronted with a new component editor down here, a new option to toggle on spatial results. The spatial interval can be anything equal than or greater than the computational interval. Right now I'm using 15 minutes, but my boundary condition information is supplied as an hour. So I'll set that spatial interval to an hour. Let me recompute. And now I'm actually going to write out the spatial results. So gridded precipitation, gridded loss, gridded excess. I'm going to write all that stuff out to an HDF file that I can then query and look at. This drop-down menu has now become enabled. So I can click that and I can see the time series and grids that are available for looking. So maybe you want to check out incremental precipitation. I just got to process some animation tiles the first time. Once that's in here, now I can start to click through and see precipitation as it traverses throughout the watershed. Right, so each one of these grid cells gets a unique time series of precipitation. Consequently, they also get a unique time series of excess too. So I can compute loss in each one of these grid cells. So let me toggle through here so you can see precipitation is falling over here. It's infiltrating in these areas, but it's not actually falling over here. So I don't get any loss over on that side. That's what you don't get in time series. The things that we display here. So if I click on this subbasin and display the time series, all you're seeing is a basin average representation of precipitation and excess. Here you actually get the spatial distribution of precipitation. Depending upon the model choices, you may get more than this. So for instance, if I'm doing temperature index snowmelt, I'll get additional variables for snow water equivalent, melt rate ATI, some other stuff. If I'm doing two-dimensional flow, I'll also get additional variables for hydraulic depth, velocity, water surface elevation, so on and so forth. So I want to show you really, really quickly how to use two-dimensional flow within HMS as well. So I have this existing basin model here. I want to actually use 2D flow here instead of, for this subbasin here, instead of unihydrograph theory. Right now, this is using the Maud-Clark unihydrograph method. Instead, I want to use 2D flow. So I'm going to create a copy of that, and I'm going to change this to Mahoning Creek 2D. That's the name. Now I've made a carbon copy of that basin model. Let me change the way that that terrain is actually shown, change draw properties, go down to elevation Swiss. I know I did that really quick. If anybody does have questions about that, please let me know how you do that. Now I've got this basin model. I want to change this to 2D flow again. So I've gone through the trouble of already creating this mesh in RAS. RAS has like 10 years of lead time for developing meshes. So you can use break lines, you can use refinement regions. You can manually move vertices all around. You can do all sorts of really cool stuff. So I built my mesh in RAS. It was beautiful. I can do all that. Now I can import it into HMS. So I'm going to go to File, Import, HEC-RAS HDF file. And now I need to select the HDF file. This is specifically, I need the plan HDF file, so I need to do a dummy run in RAS to generate that since I need some boundary condition information there. I have that. Let me select it. I'll click Next. Now I choose the basin model that I want to import to. That's Mahoning Creek 2D, the one that I just created. Now I need to choose a sub-basin that I want to import to. And that's Mahoning Creek. That's this guy here. Click Next. Now within that HDF file, I cracked it open and I said, all right, there's one 2D area within there, has 3,300 cells, there's 2 boundary condition lines. Is that the one you want? Yes, and that is the one that I want. I click Finish. I actually import. Now I'm using that 2-dimensional flow area as opposed to the Mod Clark information, the grid cells from before. This routing reach is no longer needed. So let me go ahead and delete that because I'm going to connect this confluence, which takes flow from this subbasin and this subbasin, combines it together, and now I'm going to route it through this 2D area. So I'm going to select my inflow. This is a 2D connection that's right up here. I can show you guys that in a second. And then select this subbasin, expand this node. Now in the discretization node, it's changed to unstructured. I can select my 2D connections. This is on the downstream side, normal depth boundary condition down here. I'm going to select that and say I want to pipe the results to the gauge. You can have bifurcations. So you can have flow come out of one side to one area, out of another side to the other area. It all does the exact same thing, pipes those results out. And I also want to apply all my base flow to this guy here. I'll click Save. I'm going to create a new simulation. So I had September 2018 before, but now I'm doing 2D, so I'll call it September 2018_2D. Select the basin model of interest, the meteorologic model of interest, and the control specifications. They're all ready to go. And the MET model, I do need to say, hey, I want to use that specific basin model that I used here before. So I changed that to yes. And now, oh, one more thing. I want to go to compute. And now in here, I want to also toggle on spatial results because I want to show you the new results that you can actually get. I'll say 1 hour here, and I'm ready to compute. So I go ahead and compute that. And now it's rocking and rolling. This is using the exact same compute engine that is used within HEC-RAS. The really, really cool thing about that, when they make improvements there for speed improvements, so just last week, we found inefficiencies in the sediment, 2D sediment compute engine. That was changed. Now we actually get like a 50% increase across the board. When we make advancements, which came out of this 2D sediment work, they benefit. So it's a back and forth thing where we share the same library, everybody benefits and everybody gets the same bang for the buck, right? It's not just shared with one application, now we see it across the board. Within the Corps of Engineers, we typically use 2D flow only where it's necessary, right? This is a computationally intense process. You can see how slow this compute is progressing. Hydrograph theory is snappy, really, really fast like that. 2D flow, not so much. This is supposed to be used in like when you only need it, right? So we do this for dam safety studies when we're looking at hydrograph peaking, where I have to extrapolate way out to the probable maximum precipitation. And I need to apply 20 times more precipitation than I've ever seen. Hydrograph theory doesn't cut it in that case. Or I have really complicated areas. One that I want to show you here is a tutorial and guide that we have on our webpage that you can check out. This is the Truckee River watershed. Within the Truckee River watershed, the major metropolitan area is Reno and Sparks. There's about 500,000 people or so that live there. And it's located in this bowl-shaped area right here. So throughout the entire watershed is super mountainous. You can see from the color coding, but it's really flat right here. I want to use 2D flow because water can get out of bank there and go everywhere. So what I did in this case was I merged these 3 subbasins together. I don't need them to be individual elements anymore. I want them to all be a single one because I'm going to represent that with a 2-dimensional flow area. So if I zoom in there, now I just have one. And if I turn on discretizations and show you that, I'm going to use hydrograph theory everywhere else, but I'm going to use 2D flow right here. And I'm going to do temperature index snow. I'm going to do evapotranspiration on there so I can extract water that's been infiltrated into the mesh, into the soil, take it back out again and make room for more water. I'm going to also do transform across the overland plain. I'm going to do base flow within there too. Let me show you some of the cool results that you can see here. Oh, and by the way, this compute just finished, so it's like a minute and a half or so to compute something like that. But you get really cool pictures out of it. I'll just cut straight to the chase and look at hydraulic depth, something like this. So I can animate the way that water is distributed on the overland plain. So we got water all over the place, snow is melting. Really, really cool stuff that you can look at Let me look at average cell velocity. So you can start to see, okay, water is flowing through the Truckee River pretty quickly. Then rain starts falling, snow starts melting, and you start to see water flowing out of the mountains, right? So this is Mount Rose ski area over here, super steep. You can see preferential channels that flow through there. You can start to visualize all sorts of stuff when using 2D flow in here. This compute was a little bit longer. This one takes maybe like 4 minutes, something like that, 3 or 4 minutes. There's a ton of cells in there, but lots of cool stuff in here. So I'll stop rambling at this point. I want to finish up and let Martin have a couple of minutes to talk about this really quickly. For our international users, we do have interface translation capabilities within HMS. So about 95 language countries and locales are supported. So if you want to translate the interface, use different decimal formats, whether you're using periods or commas, you can do that in here. There's a live link there. You can check that out. Some upcoming features that we're interested in, more GIS tools. Tommy's cranking them out. We got a whole bunch of team members that are cranking out really useful GIS tools. Our goal is to get you away from using any GIS to build or create or use an HMS model. That's what we're trying to get to. We want to handle gridded data better. Right now we can import NetCDF, GRIB files, ASCII, BIL, all sorts of different formats, but we want to get better with handling different gridded formats. Check out our website. Send us any that don't work that you can import. We'd love to make that work. We're adding 2D sediment transport. That's coming up soon. More optimization uncertainty analysis tools. So making risk-informed decisions is key within the Corps of Engineers. Hypothetical storm enhancements. Team member Greg is cranking away on that. More spatial results. Always want to make things faster. So on and so forth. Just want to say thank you for letting us present some of this stuff and kick it over to Martin.
Thanks, Mike and Tom. It's really exciting to see what you're up to. You said earlier you're going to blow our minds a bit, and I think you've done that. One of the questions that came up in the Q&A was, can we import the BOM rainfall data into HMS? And the answer is yes, we can now, mainly due to Chris Ryan's development of the storm injector, which will do all the things that ARNR 2019 asks of hydrological models. I'm going to touch on that very briefly. I can't give it justice, I'm afraid, because we haven't got time, but the answer to that question is really yes, we can do it. So what's new in HMS? For me, what I'm going to cover very briefly is an introduction of Storm Injector, which is, as I said, developed by Chris Ryan of Catchment Simulation Solutions. It is a commercial product. I'll refer to Chris for all the licensing and the deployment for that. I'm going to do some comparisons with RORB. RORB is a model that's used quite often in Australia. It's already set up for ARNR 2019. I'm not here to have a crack at RORB. I'm just using it as a comparison. I'm also going to talk very briefly about gridded rain. I know that our colleagues in HEC have covered that really well. And this is I think this is a really exciting development, the whole idea of grids. I'll explain a little bit why. Who am I? What am I coming from? Well, I'm an experimental user, I suppose you call me. I'm the kind of guy who picks something up and pokes it around and says, does it do this and does it do that and how does it do this? So I'm not part of the development team. I'm just somebody who's really picked it up and played with it and found out some stuff and tested the technology and with an aim of using that technology in Australia. I regard HMS as a modeling platform. One of the things, I think one of the conceptual things we need to grasp is that HMS has got a whole host of options, strategies, alternatives, and so on, which new users are going to find really quite daunting, as opposed to, well, compared to, say, RORB, which is like you put this number in, you put this number in, you get an output. It's not like that at all. It brings a lot of that technology together. And my biggest reason to push HMS and ask people to use it is it will actually teach you hydrology and reward you with some good outputs. But you need to know stuff in order to drive it, really. Comparing HMS with RORB is a little bit like comparing a screwdriver with a workshop. RORB does things one particular way. There's some kind of variations and options in there, but HMS, as I say, is more like a modeling platform. Now that presents a real challenge, like, where do you start? You need to go further afield for HMS. There's the HEC documentation, which is very thorough and very large. You need to know where to look in that stuff. There are also user guides. The ones that I'm aware of are Auckland Regional Council, TP 108, and the Harris County Flood Control District's manual. Both of those are based on event-based stuff. One's in New Zealand, one's in the US, of course. Not really touching on long-term continuous simulation, which is another interest of mine. HMS has got lots of options. There are options for loss models. So in your initial loss, continuing loss, the kind of losses that we use commonly in Australia are one of the many options. There's transform models, and this is all about changing the rainfall into a hydrograph. Like there was talking about unit hydrographs and so on. Link rounding, different things you can do with the links. Like Rob, of course, HMS has options for reservoirs, and there's a number of things you can do with those things. Also, another conceptual idea you need to get is that HMS is oriented to real space, the GIS. In fact, it's easier to set a project up in GIS than it's not. So some of the older hydrological models kind of work in a theoretical space, but HMS is real space. It's also real time, so we're dealing with Gregorian calendar. So that means leap years and things like that. HMS has advanced capabilities for parameter optimization, which is useful when you're calibrating, and also Monte Carlo. So looking at some of these options, this is simply a comparison of some of the outputs on actually an earlier version of HMS with a RAW output. So the RAW output is the black line, and the HMS output's the blue line, and they're just superimposed one on top of the other. And at that time, we had these 4 different types of things, and I was just saying, okay, what's going to provide us with a similar output to RAW? You see that the Clark unit hydrograph and the SES unit hydrograph do a pretty good job. Kinematic wave, perhaps less so in this case, and the Snyder less so. Now, it's not saying that one is right or one is wrong, but if you're looking for a comparison with RAW, then those unit hydrographs obviously give you a fairly good match. A couple of examples I'm going to look at. This is the Rufus Street gauge in Darebin Creek in Melbourne. The map there on the right of screen shows the river gauges in orange and all the rain gauges in blue. You can see where the catchment is. That catchment I delineated using the tools within HMS, by the way. And if you don't use HMS for anything else, the catchment delineation tools are actually really powerful. Sources of data here from Oral Online, the Elvis Elevation Data Portal for Australia, and Bomb Data Water Online gives you the stream gauges and some of the rain gauges. In this case, I was just doing a single node model reporting to the gauge, and basically looking at how we develop it. Now, unfortunately, I've only got one slide for catchment sim. It really doesn't for the storm injector. I'm afraid I can't go through the whole lot on this. But what this shows is that Chris Ryan's done a great job in setting up the storm injector so we can use HMS for AR&R. And that means dealing with all your initial losses, continuing losses, and pre-bursts and so on. This is the output after running all of the storm ensembles. And of course, you get the box and Wistica plots, the critical storm, and so on. You can do it for all the AEPs. So I'm looking at the 1% AEP at the moment. There are more than just the initial loss and continuous loss parameters to optimize within the model. We're also looking at the unit hydrograph parameters as well. And I use the HMS tools to optimize those. I think this is a little bit of a lucky strike because I looked at a single historic storm. The flow hydrograph for that shown in black on the bottom of the plot there, and the HMS output is shown as blue. The top is the pluviograph. And as you can see, you can get a pretty good result. So once you've calibrated all those parameters, we're getting a fairly faithful reproduction of what's actually happening at the gauge. So that to me is telling us that the model is a fairly good representation of the real thing, which is what calibration is all about. This is a plot using various options. And again, I'm looking at simply comparing the HMS outputs with RAW. The red line is what we're looking for. So this is the red line is the flood frequency analysis at the gauge. And this has come directly from the gauge record, which is about 34 years, no, maybe more than that, sorry, if I get my maths right. And of course, you can use HEC-SSP for the analysis, the flood frequency analysis. You can also use FLIKE and so on. So we're trying to aim at the red line. The green dotted lines are the confidence limits. And what this is showing you is that over the AEPs, the raw outputs are shown as the gold diamonds, if you like. HMS, the blue triangles, are those with the temporal patterns. And then I did something that AONR tells you doesn't recommend, which is to put uniform flows in. And that's basically putting the rainfall intensity over the duration as a single intensity, rather than the temporal patterns. Got fairly close results to the HMS with the temporal patterns. You can draw your own conclusions from that. We're getting very good results from HMS for above the 10% AEP and rarer. Less so for less than 10% AEP and rarer. And this is just using the initial continuing loss model. And if I were to develop this a bit further, I might take a further look at those, how those losses are operating. And this is with a single set of initial and continuing losses, by the way, set up, apart from the HMS, actually apart from the storm injector outputs there. Another example is looking at the Kimberley in Western Australia, again using data which is available online. We've got a catchment reporting to the gauge 707005 at Toolunga, Cane River at Toolunga. The nearest rain gauge is on Onslow Airport, and that's about 65 kilometres away. Now, you can imagine that there's going to be a big variation in rainfall between the rain gauge at the airport and what's happening on the catchment there. This is an area which is not very well gauged, so you've got a lot of sparse data. It's also an arid area as well. Now, I was looking at the technology here. We don't have access, obviously the US rainfall gridded data doesn't extend to Australia. So I was looking around for sources of rainfall data. And I found one possible source in the ERA5 gridded rain that's published by the European Space Agency. Critically, it's at 1 hour intervals. I had to do some pretty heroic adjustments to kind of calibrate it to what's going on at the rain gauge. As you can see there, there's a cell sitting over the rain gauge. And of course, if you know what the time series is in the grid in the cell, you can compare it to what's happening at the rain gauge and therefore do some adjustments. But this screenshot there is simply 1 hour cumulative precipitation over that particular grid. And you can see how that relates to the catchment, which has been delineated in HMS. Again, what I'm doing here is I'm just proving the technology, just saying, how do we use the technology outside the US using publicly available information and data? So after a bit of discretization and further parameter optimization, so we're getting a pretty good match on peak flows and the rising and falling limbs, but we're missing out on some of those smaller peaks either side of the big peak. And the reason for that is it's just not available in the data there. Now, why I say this is cheap is because it's a calibration to a single event only. And of course, I made the answer fit the question on that particular thing, but it proves that the technology is available. You also need to use those grids over areas where you don't have the gauges. This is what I was running at 4 long-term continuous simulations, what I call this is a combined rating curve. And it's to help us to decide which levels to put bridges and roads at for the road crossings. And you can use this kind of graph to relate both the rating curve, the elevation of the road with the frequency that the road gets flooded, and that's the AEP, and also the duration. Of course, you can plug that back into your economic model and decide how high to put your bridge. There are other ways of demonstrating this, but the reason I'm flashing this on the screen is to show that this is actually a direct output of long-term continuous simulation. It doesn't actually go through another kind of statistical model to produce this. So in conclusions, we have the technology. Well, HMS gives us the platform. I think one of the things that really excite me about HMS is that you can draw in lots of different kinds of technologies. You can draw in gridded rain, you can draw in long-term continuous, you can draw in your event-based models, and it's in the same platform, the same space. So you can make those comparisons and do those adjustments within the same model. So you're comparing apples with apples. It's not difficult to calibrate to a single event, but it's much more difficult to calibrate to a range of events. And this is what we want to get to, of course, is something that represents the reality. And the reality is going to be responding to those intense events as well as those minor events. And to me, a perfect model is something that represents, is scalable over that entire range. To get meaningful calibration to the gauges, the biggest current need is for 1 hour long-term rainfall series. It's quite difficult to find. It's hard enough to find 1 hour point data. There are ways of doing it, or even at smaller increments. And what I was looking at was 1 hour gridded series. Now, I've also, since doing that previous work in the Pilbara, we've been talking to the Bureau of Meteorology, and they are in the process of publishing the Barra grids, which will be available on request to users. And those grids are 1 hour rainfall grids, so there's also other climate data in there. And I think that's a really major step forward because it gives you a single point of reference to get stuff from. that you can use for the whole of Australia. I didn't use the Barra grid. I'd use the European stuff, mainly because it was free and also because it's a 1 hour interval. But you need that short time interval to get that meaningful calibration to the gauges. If you imagine your catchments are going to respond over a period of hours. With the gridded data, you can calibrate any catchment at any scale. And we can talk about refinements to the grid, about smaller grid cell sizes, time intervals, and so on, about how to calibrate those grids to what's happening on the ground. But you can see the future in this. The grids can mean that your data you can get all your data from a single source. And I know the HEC has been developing this technology so that you don't just need grids for rainfall. You can do it for evaporation. You can do it for your soil losses. You can do it for your fractions impervious. You can do it for all your soil parameters and so on. So the future for modeling, my little catchphrase, the future is gridded, really is about taking those grids and sort of layering them up like a club sandwich and combining them into something that gives you an output. And we can do all sorts of things with those grids once we've got them. But the rainfall grids are the start, and HMS has the capability to do that. And that concludes my quick overview. Thanks.
Sounds good. All right. Thanks, Martin. I think my video is not coming on very well here either. So, but if you wanted to come on with the audio, any questions that you've answered through the chat line, let us know. And maybe we'll start going back through the order of things. But we haven't heard from Chris yet. Has anything come on the chat line that you've addressed that you wanted to highlight? And then we'll just have everybody highlight at least one question. So we will go past the hour. If you need to run, that's you will have this recording. So we're going to just stay on board for about 10 minutes here and have some discussion with the panelists and presenters. If you do need to run, do fill out that survey for us and have a look at the additional resources that are available for you. I will stop my share here and get back to the panelists then. Over to you, Chris.
Oh, thank you. Look, it was really interesting to see that presentation and all the capabilities in HMS. I'm relatively new to the software myself, so thank you for that. As far as the Australian context goes, just wanted to say that we do have this support now to be able to do the R&R 2019 modelling in that. So hopefully that allows people to use it in Australia. But I guess that's the easy part. Now the challenge is to get a lot of calibrated models built in Australia and really demonstrate that HMS is just as good, or if not better, than the tools we've been using for the last decades here. So that's the challenge ahead of us. But this is really just to get our quite complicated design storm methodology into HMS, and that's what Storm Injector can now do. And yeah, on that page there's a little 3-minute video of how that works. We're still working with the HEC team to get some little bugs resolved, but yeah, it's pretty much operational at this point.
Sounds good. Over to you, Matt. Let's have you answer a couple of questions, anything that's come up on the chat line while you were sitting in the background, especially those that have been upvoted the most, if you want to highlight any questions that you've hit.
Yeah, the one I want to highlight, it's about options, and I love options. And what Tom and Mike showed today is they showed the use of terrain data and using that terrain data to delineate a watershed, right? And what I like about one of the features in HMS is, let's say you've already done that using some external tool, or there's an existing model already out there, and you want to reuse those delineations from subbasins and reaches. And so in one of the questions, and we posted the link to a tutorial for that question, you can import shapefiles. So if you had the shapefile of your subbasin polygons and your river reaches, you could import those as GIS features in HMS, and then link those together to quickly create a basin model schematic that matches some existing model that you want to reproduce similar results in HMS. So I just wanted to point that one out.
Sounds good. And I think one of the most common questions, or something that everybody seems to be interested in, HMS and RAS seem to have some features that are in common. And if you look at the chat line, and these will be posted with the resources as well, these questions and answers, there are quite a few things where the answer was yes, yes, this is coming. Similar map layouts and Google Earth and everything else, being able to turn all those things on and off, similar to what you can do in RAS. That is coming. One of the big questions is, will they all be together as one product someday, where you just open up one GUI and there you see them both. Who else? Let's see, Tom, you've got your microphone on, and Michael's giving the crossed fingers. Any responses to that question?
That's a dream of mine. It's a career goal for sure.
Oh, good. All right, so we can look forward to that in one of the future versions. Just make sure everybody's had a chance to weigh in on a couple of those questions. Martin, anything that you answered during the HEC presentation that you wanted to highlight for the audience?
It's really interesting to see Mike and Tom's presentation there. I think the main thing for Australian users is that you've got this daunting array of options. And Chris in his answer kind of alluded to it a little bit. We've set it up, or rather Chris has set it up for ARNR 2019, which gives us something of a loss model to work with, but that's just the beginning. You've still got to go through your transform parameters and other parameters in the model and so on. We don't really have a standardized way of working in Australia with HMS because we've got to think about those things. I think hopefully that will emerge if people are going to be using this thing a bit more, that we'll have like, this is the way you set up your unit hydrographs, or this is how you do your link routing and so on, because we've got good results tested already. One thing this platform does do is it gives the power to the user to actually start messing around with those things. So you can, again, you have to, as coming back to my comment on, it teaches you hydrology. You've got to work it out, and but you've actually got the capabilities with an HMS to actually start to experiment and to see what gives you better answers and worse answers, and so on. I just also like to comment that as someone who's not been, I don't have any commercial interest with catchment simulation solutions. I'm not a developer or whatever, but it really does, to go to Storm Injector really is going to save you an awful lot of time. I've tried to put in those temporal patterns manually into DSS and so on. It takes you, maybe takes you a week to get one thing set up. So one real advantage that Chris has brought us is that you can now do this really rapidly. It works really well, sorry. And that's one of the reasons why you should try Storm Injector rather than doing it manually. You're just going to drive yourself nuts putting in those storms manually.
No, thanks a lot. Sorry, my camera's glitching here, but Michael, anything that you wanted to cover that you've hit on the chat line?
Just great questions all around. Really appreciate the interaction. I think I inadvertently set one to answer live. I think it was due to the version. It was a question that was related to the version. So we were using a beta version 4.9. It's on our website if you want to download it. Like Tommy said, we give you access to the betas if you want to try and test new things. No admin rights are needed to use them or anything like that, so you can use them on your Army Corps of Engineers computer if you want to. But we were using a beta version. If you want to use a more stable release, look to version 4.8, but we'll be releasing version 4.9 soon. We try and make releases as rapidly as possible.
Great. All right, so we'll need to wrap this up in the next couple of minutes here. Let's just have closing remarks from everyone. And again, just anything you'd like to add before we log off here. Maybe let's go back in the same order we just did. Go back to Matt, and we'll just go through the order that way. Any closing remarks?
Yeah, last thing for me is please take a look at those tutorials and guides. We've invested some time to add those that really line up with the new features in the software. So if you're interested in some new feature, I'm sure we have a tutorial that will show you a data set and how to apply that new feature.
Good. All right, Chris, anything to wrap it up?
No, just thank you to all the presenters.
Good. All right, Tom?
Yeah, thanks again for having us. I would say, like Matt, take a look at the tutorials and guides. And then again, the offer is open. If you feel like you have something to contribute, we're happy to hear from you. So if you have a tutorial and guide for, say, Australia that you think would be valuable to others, feel free to send it our way, and we'll try to see to it that we can post it to our website. Yes,
they're very responsive. Martin, any final comments?
I'm a fan, so please forgive me. I'm going to rant on about this. I think HMS is a great platform. It brings together those technologies. You can do those comparisons between all those different types of modeling strategies and outputs and so on. And the fact that it's free, it's available, is brilliant. So, and thanks for Tom and Mike and all of the HEC for developing it and sharing it with us.
Yeah, and thanks for the responsiveness here. Mike, we'll let you close off, and then we'll move into some final slides that show you the resources available to you for future Australian Water School work. So Mike, oh, your cat's gone. I thought your cat.
Yeah.
Give us the final send off. Awesome. So yeah, any final words?
I just want to say thank you guys again for the opportunity. We love being able to present to this user base. Really appreciate it. Any cool international applications, like Tommy was saying, Matt was saying, please send it our way. We love to publish things on our website that other people can benefit from and learn from. Always looking forward to that. So thank you.
Thanks. Well, on behalf of the international community of freeloaders here, let's thank the American taxpayers for funding the software for us. We are greatly benefiting from it here. So for everyone attending, you will get this recording link. Please do take this short survey that will pop up when you log off. Let us know what you'd like to see more of in our future resources that are coming up. So with that, you'll see a list here of future courses that are coming up. Do sign up for those, stay subscribed so that we can stay in touch. And if you want more of what we've just talked about, we will in November be holding a HMS course. Details on that will go out to the subscription list for this webinar, and we look forward to interacting with you there. If you want to hear something specific about Australia, we'll probably do a separate module just for that, and then one more general one for HMS. So let us know what you'd like to see more of. With that, I will sign off. Thanks so much for your participation, and we will see you next time. Bye-bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.